Welcome to this comprehensive module on containerization in our DevOps course. Containerization has become a cornerstone of DevOps practices, enabling organizations to streamline their development and deployment processes while ensuring consistency across different environments. In this module, we'll explore everything from the fundamental concepts of containerization to its practical applications in real-world scenarios. You'll learn how containers work, why they've become so essential in modern software development, and how to effectively implement containerization in your own projects. By the end of this module, you'll have a thorough understanding of containerization technologies, like Docker and Kubernetes, and you'll be equipped with the knowledge to make informed decisions about container adoption in your organization. Whether you're new to DevOps or looking to enhance your existing skills, this module will provide valuable insights into one of the most transformative technologies in software development. Let's begin our journey into the world of containerization. Let's start by understanding what containerization truly means in the context of modern software development and DevOps practices. Containerization represents a fundamental shift in how we package and deploy applications, and its importance cannot be overstated. Think of containerization as a modern shipping container for your software. Just as shipping containers revolutionized global trade by providing a standardized way to transport goods, software containers provide a standardized way to package and deploy applications. This seemingly simple concept has profound implications for software development and deployment. The key characteristics we'll discuss, lightweight nature, portability, and isolation, are what make containers so powerful. When we say containers are lightweight, we mean they contain only what's necessary for your application to run, unlike traditional virtual machines that include entire operating systems. This efficiency translates into faster deployment times and better resource utilization. Portability is perhaps one of the most valuable aspects of containerization. Consider the classic developer phrase, "but it works on my machine." With containers, this problem essentially disappears because your application runs in the same container environment regardless of where it's deployed, be it a developer's laptop, a test server, or a production cloud environment. The isolation aspect of containers provides a crucial security benefit while also preventing dependency conflicts. Each container runs in its own isolated environment, with its own file system, network interface, and process space. This means that even if one container is compromised, others remain secure, and applications with conflicting dependencies can run side by side without issues. As we progress through this module, you'll see how these characteristics come together to solve real-world problems in software deployment and scaling. You'll learn not just the what and how of containerization, but also the why, understanding the business and technical drivers that have made containerization so essential in modern software development. Let's dive into what containerization really means and why it's become such a fundamental concept in modern software development and DevOps practices. Containerization is essentially a method of operating system virtualization that delivers software in packages called containers. These containers are completely isolated environments that bundle together everything needed to run an application: the code, runtime, system tools, system libraries, and settings. Think of it as creating a complete, self-contained unit that can run anywhere, consistently and reliably. The lightweight nature of containers is one of their most significant advantages. Unlike traditional virtual machines that include entire operating systems, containers share the host system's OS kernel and only include the additional components needed to run the application. This makes them incredibly efficient in terms of resource usage and allows them to start up almost instantly. Portability is another key feature that makes containerization so powerful. When we say containers are portable, we mean they can run on any system that supports the container runtime, regardless of the underlying infrastructure. This solves one of the most persistent problems in software deployment, the "it works on my machine" syndrome. Whether you're running the container on a developer's laptop, a test server, or in a cloud environment, it will behave exactly the same way. The isolation aspect of containerization provides multiple benefits. Each container runs in its own environment, completely isolated from other containers and the host system. This isolation enhances security by containing potential security breaches, prevents conflicts between applications, allows different versions of the same software to run side by side, makes it easier to manage and monitor resource usage. As we progress through this module, you'll see how these characteristics of containerization, lightweight, portable, and isolated, come together to transform how we develop, deploy, and manage applications in modern software development. The history of containerization is a fascinating journey that spans several decades of computing innovation. Let's explore this evolution to better understand how we arrived at today's container technologies. The story begins in 1979 with the introduction of chroot in Unix version 7. This was the first implementation of process isolation, allowing an administrator to create a virtual root directory for processes, effectively isolating them from the rest of the system. While primitive by today's standards, chroot laid the groundwork for modern containerization concepts. The early 2000s saw significant advances with FreeBSD jails in 2000 and Solaris zones in 2004. FreeBSD jails extended the chroot concept by adding process isolation and network resources partitioning. Solaris zones introduced the concept of complete operating system-level virtualization, allowing multiple isolated environments to run on a single operating system instance. Linux containers, LXC, emerged in 2008, bringing similar capabilities to Linux systems. LXC combines several Linux kernel features, including C groups and namespaces, to provide a more complete containerization solution. However, while powerful, these early container technologies were complex to use and required significant expertise. The real breakthrough came in 2013 with the introduction of Docker. Docker's innovation wasn't in creating new containerization technology. Instead, it made existing container technology accessible and user-friendly. Docker introduced several key concepts that transformed how we use containers. First, it introduced a simple and intuitive command line interface that made container creation and management straightforward. Second, it created a standard format for container images, making them easily shareable. Third, it established Docker Hub, a central repository for sharing container images. What's particularly interesting is how Docker's timing coincided with the rise of microservices architecture and DevOps practices. This convergence created a perfect storm that accelerated container adoption across the industry. Companies like Google, which had been using container-like technology internally for years, began sharing their expertise and tools, leading to projects like Kubernetes. Understanding this history helps us appreciate why certain design decisions were made and how containerization has evolved to address real-world challenges. As we continue through this module, you'll see how these historical developments influence modern containerization practices and why certain approaches have become standard in the industry. Let's examine why containerization became such a critical need in modern software development by looking at the challenges it addresses. These challenges were not just minor inconveniences, they were significant obstacles that affected development velocity, deployment reliability, and ultimately, business success. The first major challenge was dependency conflicts. In traditional deployment models, applications would share the same operating system environment, leading to what developers often called dependency hell. Imagine having two applications, one requiring Python 2.7 and another needing Python 3.8. Without containerization, running both applications on the same server would be problematic. Environment inconsistencies were another critical issue. The phrase, "works on my machine," became infamous in software development because applications would behave differently across development, testing, and production environments. These inconsistencies led to bugs that were difficult to reproduce and fix. For example, a developer might use the latest version of MongoDB locally, while the production environment runs an older version, leading to subtle behavioral differences that only appear in production. Deployment complexity was perhaps the most time-consuming challenge. Each application came with its own set of installation instructions, configuration requirements, and dependencies. System administrators often had to maintain detailed documentation for each application's deployment process, and even then, deployments could fail due to missteps or environmental differences. These challenges had real business impacts. Development teams spent excessive time debugging environment-related issues instead of building features. Operations teams struggled with maintaining consistent environments across different stages. Deployment processes were error-prone and often required manual intervention. Scaling applications required significant planning and effort. Rolling back problematic deployments was complicated and risky. Containerization addresses these challenges by providing a standardized way to package and deploy applications with all their dependencies. It creates a consistent environment across all stages of development and deployment, significantly reducing the "it works on my machine" problem. The isolation between containers means that dependency conflicts become a non-issue, as each container has its own isolated set of dependencies. As we proceed through this module, you'll learn how to leverage containerization to solve these challenges in your own development and deployment processes. You'll see practical examples of how containers can simplify your workflow and make your applications more reliable and easier to maintain. Let's dive deep into the benefits of containerization, exploring how each advantage translates into real-world value for development teams and organizations. First, let's discuss portability. When we say containers are portable, we mean they can run consistently across any environment that supports the container runtime. This portability has profound implications. Developers can work with production-like environments on their local machines. Testing becomes more reliable as the test environment exactly matches production. Deployment to different cloud providers becomes straightforward, avoiding vendor lock-in. Disaster recovery becomes simpler as containers can be quickly redeployed on new infrastructure. Scalability is another crucial benefit. Containers start quickly and can be automatically scaled based on demand. This means applications can handle traffic spikes efficiently. Resources can be utilized more effectively. Costs can be optimized by scaling down during low traffic periods. High availability becomes easier to achieve through container orchestration. The isolation provided by containers brings several advantages. Security is enhanced as vulnerabilities in one container don't affect others. Applications with conflicting dependencies can run side by side. Resource usage can be controlled and monitored at the container level. Testing becomes more reliable as each container provides a clean environment. Efficiency is a key benefit that directly impacts the bottom line. Containers share the host OS kernel, using fewer resources than traditional VMs. Startup times are typically seconds rather than minutes. Development cycles are shortened due to consistent environments. Resource utilization is improved through better density and scheduling. Reproducibility is perhaps one of the most underrated benefits. Every deployment uses exactly the same container image. Development environments can be quickly recreated. Bugs can be more easily reproduced and fixed. New team members can get started quickly with minimal setup. In practice, these benefits combine to create significant improvements in development and operations. Reduce time to market for new features. Lower operational costs through better resource utilization. Improved application, reliability and stability. Enhanced security through isolation and immutable infrastructure. Greater flexibility in choosing infrastructure providers. As we continue through this module, you'll learn how to leverage these benefits in your own projects and how to maximize their value through proper container implementation and management strategies. Let's examine the key components that make containerization possible. Understanding these components is crucial for effectively working with container technologies. Containers themselves are the fundamental building blocks. Think of a container as a standardized package that includes everything needed to run an application: the code, runtime, system tools, libraries, and settings. What makes containers special is their isolation. Each container runs as an isolated process in user space on the host operating system. This isolation is achieved through Linux kernel features like namespaces and C groups. The container engine is the software that manages these containers. It's responsible for creating and destroying containers, managing container lifecycle, handling networking between containers, managing storage and volumes, implementing security policies, providing APIs for container management. Docker engine is the most well-known container engine, but others like Containered and CRIO are also widely used. Each engine implements standard container specifications defined by the Open Container Initiative, OCI, ensuring compatibility across different container technologies. The relationship between these components is crucial to understand. The container engine interfaces with the host operating system. Containers run as isolated processes managed by the engine. The engine provides APIs that tools and orchestrators can use to manage containers. As we progress through this module, you'll learn how to work with these components effectively, understanding their roles in building scalable, maintainable, containerized applications. Let's explore the landscape of containerization technologies, focusing on the most widely adopted solutions and their specific strengths. Docker stands as the most prominent container platform, and for good reason. It provides a user-friendly command line interface, excellent documentation and community support, a vast ecosystem of pre-built container images, tools for building, testing, and deploying containers, integration with most development and deployment tools. Kubernetes has become the de facto standard for container orchestration. It offers automated container deployment and scaling, self-healing capabilities, load balancing and service discovery, rolling updates and rollbacks, advanced networking and storage options. Alternative container technologies like Podman, LXC, and Containered each serve specific needs. Podman offers a daemonless architecture and rootless containers. LXC provides system containers that are closer to traditional VMs. Containered serves as a core container runtime used by both Docker and Kubernetes. Understanding these technologies and their appropriate use cases is crucial for making informed decisions in your containerization journey. As we continue, you'll learn how to choose the right tools for your specific needs and how to effectively use them in your DevOps practices. Let's explore the practical applications of containerization through real-world use cases that demonstrate its value in modern software development and deployment. Application. Deployment represents the most common use case for containerization. It simplifies the deployment process by ensuring consistency across different environments, reducing deployment-related errors, enabling rapid rollbacks when issues occur, simplifying dependency management, facilitating continuous deployment practices. Microservices architecture has become synonymous with containerization because containers provide natural isolation between services, independent scaling of individual services, easy deployment and updates of single services, efficient resource utilization, technology stack flexibility for each service. DevOps practices are enhanced by containerization through automated testing in isolated environments, consistent development and production environments, rapid iteration and deployment cycles, infrastructure as code practices, simplified collaboration between development and operations teams. These use cases demonstrate how containerization can transform software development and deployment processes. As we proceed, you'll learn how to implement these patterns in your own projects and understand the best practices for each use case. Let's examine how organizations are adopting containerization and the impact it's having on modern software development practices. Cloud-native applications have become the standard approach for new software development, with containerization serving as a fundamental technology. This adoption is driven by the need for scalable and resilient applications, requirements for rapid deployment and updates, multi-cloud and hybrid cloud strategies, microservices, architecture, adoption, DevOps culture and practices. DevOps transformation is often catalyzed by containerization adoption. Organizations find that containers bridge the gap between development and operations, enable automated testing and deployment, improve collaboration and communication, reduce time to market for new features, increase overall system reliability. Hybrid and multi-cloud environments benefit significantly from containerization through consistent application behavior across different platforms, simplified migration between cloud providers, reduced vendor lock-in, unified deployment processes, efficient resource utilization. As we continue through this module, you'll learn how to plan and implement container adoption in your organization, understanding both the technical and organizational challenges involved. While containerization offers numerous benefits, it's crucial to understand its challenges and limitations. Let's examine the first set of drawbacks that organizations might face when adopting containerization. Complexity is often the first challenge organizations encounter. This manifests in several ways. Additional layers of abstraction to manage. New tools and processes to learn and implement. Complex networking configurations. Storage management challenges. Security considerations across the container ecosystem. The learning curve can be steep for teams new to containerization. Teams need to understand container concepts and best practices. Operations staff must learn new monitoring and debugging techniques. Developers must adapt to container-based development workflows. Security teams need to understand container-specific vulnerabilities. Architecture teams must rethink application design patterns. Orchestration. Complexity is particularly challenging. Kubernetes has a steep learning curve. Cluster management requires specialized knowledge. Networking configurations can be complex. Storage management needs careful planning. Service mesh implementation adds additional complexity. Resource overhead, while less than traditional VMs, still exists. Container runtime overhead. Network overlay impact. Monitoring and logging overhead. Orchestra. As we continue through this module, we'll discuss strategies for addressing these challenges and making informed decisions about containerization adoption. Let's continue examining the challenges of containerization by looking at the second set of important drawbacks that organizations need to consider. Networking challenges often become apparent as container deployments scale. Complex service discovery requirements. Network performance overhead from container overlays. Cross-host container, communication security. Load balancing configuration complexity. Multi-cluster networking challenges. Security concerns require careful attention. Shared kernel vulnerabilities can affect multiple containers. Image security and vulnerability scanning become critical. Runtime security monitoring needs special attention. Access control and secrets management. Complexity. Container escape risks must be mitigated. Application design. Considerations can be significant. Not all applications are suitable for containerization. Stateful applications require special handling. Legacy applications may need significant refactoring. Microservices. Architecture may introduce new complexities. Service communication patterns need careful planning. Persistent data management presents unique challenges. Container ephemeral nature conflicts with data persistence. Volume management across container hosts. Backup and recovery procedures become more complex. Data consistency in distributed systems. Storage performance considerations. Understanding these drawbacks is crucial for making informed decisions about containerization adoption and planning appropriate mitigation strategies. As we proceed, we'll discuss best practices for addressing each of these challenges. Now that we've explored the fundamentals, benefits, and challenges of containerization, let's dive into the technical architecture that makes it all possible. In this section, we'll examine the building blocks of container systems, how they interact with each other, and how they work together to provide the features we've discussed. Understanding container architecture is crucial for anyone working with containerized systems. Whether you're a developer, system administrator, or DevOps engineer, this knowledge will help you make better decisions about container implementation, troubleshooting, and optimization. We'll explore everything from the base operating system layer to the container runtime and how isolation is achieved through various kernel features. Let's begin this technical journey into container architecture. Let's explore the fundamental architecture of container systems and how the various components work together to provide containerization capabilities. Container architecture is built on several key concepts that work together. The host operating system provides the foundation. Container runtime manages container execution. Container images serve as templates for running containers. Container orchestration manages deployment and scaling. The layered approach of container architecture provides efficient resource utilization through shared kernel usage. Strong isolation between containers. Lightweight deployment capabilities. Flexible networking options. Scalable resource management. Understanding this architecture is crucial for troubleshooting container issues, optimizing container performance, implementing security best practices, planning container deployments, managing container lifecycle. As we continue, we'll dive deeper into each architectural component and how they interact to create a robust containerization platform. Let's examine the core components that make up the container architecture in detail. Container images are the foundation of containerization. They are immutable templates for containers, include application code and dependencies, use a layered file system approach, enable version control of entire application stacks, support efficient storage and distribution. The container runtime is the engine that powers containerization, manages container lifecycle, handles resource allocation, provides isolation mechanisms, manages networking and storage, implements security policies. The host operating system plays a crucial role. Provides the kernel that containers share, manages system resources, handles basic security, provides networking capabilities, supports storage subsystems. Understanding how these components interact is essential for effective container management and troubleshooting. We'll explore each component's role in detail as we proceed. Let's delve into how containers achieve isolation, one of their most important features. Namespaces provide process-level isolation. PID namespaces isolate process IDs. Network namespaces provide networking isolation. Mount namespaces isolate file system views. IPC namespaces isolate inter-process communication. UTS namespaces isolate hostname and domain. Name user namespaces isolate user and group IDs. Control groups, C groups, manage resource allocation. CPU usage limits and scheduling. Memory allocation and limits. Block I/O priorities. Network bandwidth control. Device access control. This isolation mechanism ensures resource fairness between containers, security through process separation, predictable application performance, clean application startup, and shutdown. Efficient resource utilization. Understanding these isolation mechanisms is crucial for debugging container issues, optimizing container performance, implementing security policies, managing resource allocation, troubleshooting container conflicts. Let's explore how containers interact with the host operating system, a crucial aspect of container functionality. The container runtime serves as an intermediary, manages communication between containers and host OS, handles resource requests and allocation, implements isolation mechanisms, controls container lifecycle, manages networking and storage. Key interaction points include system calls to the host kernel, network interface management, storage volume mounting, resource allocation requests, security policy enforcement. 4. Understanding these interactions helps with performance optimization, security hardening, troubleshooting, resource management, system monitoring. We'll examine how to optimize these interactions for better container performance and security. Let's examine the container lifecycle and the various stages a container goes through from creation to destruction. The creation phase involves pulling or building container images, configuring container parameters, setting up networking, mounting storage volumes, applying security policies. During execution, containers run application processes, manage resource usage, handle network communications, process data and state, respond to health checks. Monitoring includes resource usage tracking, performance metrics collection, log aggregation, health status checking, alert generation. The destruction phase handles graceful process termination, resource cleanup, network disconnect, volume unmounting, container removal. Understanding this lifecycle is crucial for proper container management, efficient resource utilization, effective monitoring and logging, troubleshooting issues, implementing automation. We'll explore best practices for managing each phase of the container lifecycle. We've covered a lot of ground in this module on containerization. Now is the perfect time to address any questions you might have about the concepts we've discussed. Some common areas for questions include container implementation strategies, security best practices, performance optimization, monitoring and logging, orchestration approaches. Feel free to post your questions in the course forum or discussion board. Remember, your questions often help fellow students understand these concepts better as well.